here M1 collides with M2 and compresses the spring to its maximum compression X. The figure here that we have is I have M2 connected to a spring, and here I have M1. They're moving, there's a frictionless surface. M1 is moving with velocity v1, and this is moving with velocity v2. Now, the information we're given here is that M1 is 2 kilograms and v1 is 4 meters per second. M2 is 1 kilogram and v2 is 1 meters per second. So they collide. This is moving faster than this one. So it will catch up with it, they will collide, and then the spring will be compressed. The maximum compression is X. Now, when the spring has maximum compression, the two objects are moving together with velocity v. So find v. It's a collision. Before collision, or in this instant, initially, the total momentum is m1 v1 plus m2 v2. We ignore the mass of the spring. We assume it's very light. In this situation here, both masses are moving with velocity v, so I have m1 plus m2 times v. So v is m1 v1, which is 2 times 4, plus m2, which is 1, v2, which is 1, over m1 plus m2, which is 2 plus 1. So that's 8 plus 1, 9 over 3, so that's 3 meters per second. So in this situation, when the spring is compressed to a maximum, the velocity is 3 meters per second. How do you find X? Since there's no friction here, and the objects, in fact, are not in contact with each other, they're just in contact with the spring, so no heat is produced here. And this is an elastic collision. That is, the total energy, the mechanical energy before collision equals the mechanical energy after collision. So before collision, I have half m1 v1 squared plus half m2 v2 squared. In this situation, I have both masses moving with velocity v, so the kinetic energy is half m1 plus m2 v squared, but the spring is compressed by x. So there's a potential energy in the spring which is half k x squared. So I have half times 2 times 16 v1 squared plus half times 1 times 1 squared is half times 2 plus 1, which is 3, and v squared, since v is 3, so this is 9 plus half k, and k, okay, I should give you k. Let's say k here, in fact, is, let's take it as 150 newtons per meter. So half times 150 x squared. So this is 16 plus half. Here I have minus 27 over 2 is 75x squared. This is 16, so this is 3 is 75x squared. So x squared is 3 over 75, that's 1 over 25. This means that x is 1 over 5 meters. So it's 0.2 meters. So the spring will be compressed 0.2 meters. For part C, I'll not write the answer. We have already done this in the lecture. After the mass M1, after it has lost contact with the spring, now the spring will be uncompressed. And so essentially what we have then is we have M1 and M2 moving separately. So we have an elastic collision. Now we have M1 V1 given, M2 V2 known. So what is V1 prime? What is V2 prime? Since it's an elastic collision, we have already done this in the lecture. I can calculate V1 prime and V2 prime. So V1 prime would be M1 minus M2 over M1 plus M2 V1 plus 2M2 over M1 plus M2 V2. This is what we obtained in the lecture. So knowing V1, 4, and knowing V2, 1, knowing M1 and knowing M2, I can find V1 prime. And there's a similar formula for V2 prime. You simply interchange 1 and 2 here. So that V2 prime will be M2 minus M1 over M1 plus M2, V2, and so on. So using the formulas obtained in the lecture for V1 prime and V2 prime, we can obtain the velocities after the object 1 has lost contact with the spring.